Thevenin's theorem and Norton's theorem, right? So what is the usefulness of this theorem? How is this theorem useful? What does it do? Hopefully, at the end of this particular lecture, you'll carry a different perspective on Thevenin's theorem. You've already seen Thevenin's theorem, you've already applied Thevenin's theorem, but maybe from this perspective, you may or may not have seen it. Okay, so let me just remind you, then we can have a discussion here. All right, so let's say this is a circuit. A simple circuit is given, and we would like to, it can be solved by many methods, as all of you know. And let's say we try to solve it by Thevenin's theorem. What we are looking for is the output voltage V0. Okay, so let's apply Thevenin's theorem to this particular circuit to obtain the value of the output voltage here. So what I do is, again, Thevenin's theorem you could apply in many different ways also. Thevenin's theorem, all it says is you can take a block of linear circuit, convert it into an equivalent voltage source in series with a resistor. So you could apply it many different ways. One way I'm showing you, so I could take this block that you see here within the dotted lines, and I can apply Thevenin's theorem here, right? If I apply Thevenin's theorem, which means that this whole block that you see here can be converted into a Thevenin's voltage and a Thevenin's resistance. Okay, fine. So this whole circuit then, if I apply Thevenin's theorem, can be reduced to this particular circuit here. V Thevenin, Thevenin resistance, and R5 and R6 are still there as before. Okay. Now, of course, the problem is not solved. It appears that I've taken a complicated circuit and reduced it to a very simple circuit here. A circuit consisting of how many meshes? 1, 2, and 3. A circuit consisting of 3 meshes, I've reduced it to a circuit consisting of 1 mesh. But as all of you know, the problem is not solved. I have to determine V Thevenin and I have to determine R Thevenin. So V Thevenin is we determine by open circuiting this node here, these 2 nodes here, we open circuit it. So we get a circuit like this. This is a circuit that we have to solve to determine V Thevenin. And this is a circuit that we have to solve for finding R Thevenin. We short the independent sources that you see here, and we get the circuit. And this is what we have to solve to get the R Thevenin here. So what we are saying is this problem, a 3-mesh problem, can be solved by solving a 1-mesh problem. This is a 1-mesh problem. This is a 2-mesh problem. And this one is a, what would you call? 3-mesh, 1-mesh, 2-mesh, and this? Well, you can easily see R1 is parallel to R2 is basically boils down to 1 mesh. Okay? Right? So, have you seen any gain? We've applied Thevenin's theorem once. Have you noticed any gain in terms of effort required to obtain an answer? A 3-mesh problem has been reduced to 1 2-mesh problem and 2 1-mesh problem. And you know that 1-mesh problems are what? 1-mesh problems are you can look at the circuit and write down the answer. So they are trivial. 1-mesh problems are trivial in nature. Right? So effectively, if you think about it, what you've done is you've taken a 3-mesh problem, and in effect, the complexity of the problem has been reduced from 3-mesh to 2-mesh. Because 1 mesh we are saying is almost like trivial. You can look at it by inspection, you can write down the answer. Now what I can do is, I can take this 2-mesh problem. So what you're saying, what you're seeing is that application of Thevenin's theorem, what is it doing? Is taking a 3-mesh problem and effectively reducing it by 1. You reduce 3-mesh problem and you've reduced it to a 2-mesh problem. Okay, I can take a 2-mesh problem here, then I can apply Thevenin's theorem again to this one. I can apply Thevenin's theorem to this part here, R1, R2 that you see here, this particular part. I can apply Thevenin's theorem here. So we get this one mesh circuit. But then to solve this, I need to determine VTH2 and RTH2. That requires a circuit here for finding the Thevenin's voltage here between these two nodes and for finding the Thevenin's resistance. So we've applied Thevenin's theorem once more. And what has happened? A two mesh problem becomes one mesh, one mesh, one mesh. Right? So what we are saying is the following. Every time you apply a Thevenin's theorem to a circuit, if n is the number of meshes, effectively what you have to solve in the new circuit is a circuit with n minus one mesh. You reduce the mesh by one. See, two mesh problem effectively solved, effectively reduced to a one mesh problem. So what is happening is the following. A three mesh problem was there. We applied Thevenin's theorem once and we get one mesh, two mesh, one mesh. So as I said, these are trivial to solve. You effectively get a two mesh problem. You apply it once more. The two mesh problem that you see here, it became all one mesh problem here. So Thevenin's theorem is if you have a circuit of complexity n meshes, what Thevenin's theorem is doing, every time you apply, the resulting circuit you would get is n minus one mesh. You apply it once more, you'll get n minus two mesh. And you keep on applying it. Eventually, what will you get? You'll get a circuit complexity which is basically one mesh. But you'll get lots of one mesh circuits as you saw. It's not that you have to solve one mesh circuit. You get lots of them. And so effectively what we are saying is if any complex, in principle, any complex n mesh circuit can be reduced to a series of one mesh circuit. And what we are saying is each one mesh circuit that you have, you can solve by inspection. You can simply look at it and you can write down the answer. That's that's another way of looking at what Thevenin's theorem is doing. Reducing effectively the number of meshes by one. And what we are saying is, no matter how complex the circuit is, linear circuit is, you can eventually reduce it to a large number of one mesh circuits. So either you can solve a complex 5 or 6 mesh circuit, or you can solve maybe 6 or 7 one mesh circuits. Now you have to decide which one is easier. You have to solve 6 of them, but they're all one mesh circuit. So you can very quickly write down what the answers are. But also recognize that there's an effort involved in decomposition also. You have to take it and write down the circuit and then do it again and write down the circuit. So there is an effort involved in, if we go back here, we take this and there's an effort involved in writing this, there's this here, then again here. And so eventually what you're solving is this circuit, this circuit, this circuit, this circuit, and this. So a few one mesh circuits are all that you're solving in order to arrive at the answer here. Same thing happens with nodal. The other thing, let me show you what happens when you apply Thevenin's theorem. So one is you're saying what Thevenin's theorem is doing, reducing the number of meshes by one. The other thing that happens is, see, if I apply Thevenin's theorem, what I just illustrated, and I write down the answer, this is the answer that you would get. An answer like this. V0 is V1, R2 by R1 plus R2, R4 by R4 plus R3, R1 parallel R2. Look at this expression. On the other hand, if I had applied a complete mesh analysis, write down a current I1, I2, I3, and the three mesh circuit would have resulted in 3 variable equations. If I had solved them, I would have obtained this. This one, V0. All right. I would have obtained if I had simply done it as a mathematical problem, I had taken this 3 mesh circuit, wrote down an equation I1, I2, I3, and simplified, done all the algebra, I would have gotten this expression here. So compare this expression versus this. All right. Compare the two expressions. And what is the advantage of one? Can you see that this is a structured expression? There is a structure there. It tells you that there is an R1 parallel R2. There is a voltage divider R2 by R1 plus R2. There's a structure in the answer. And the structure of the final expression is related to the structure of the circuit. If there is a R1 in parallel with R2, it does show up in this particular this thing here. Of course, I can expand this up and end up getting something as complicated as that, but that defeats the purpose. So once you do a Thevenin's or a Norton's, you end up getting a structured expression which perhaps yields more insight than this particular expression. Okay, so that's the other benefit that you get by applying Thevenin's theorem here. Let me show it to you the same thing that happens with Norton's theorem. So Norton's theorem, same problem. We have 3 nodes, and Norton's theorem, let's apply it to this part of the circuit here. So Norton's theorem, you know that the circuit you approximate by, not approximate, you transform it into a current source in parallel with a resistor. So this whole thing becomes current source in parallel with the resistor along with the remaining resistor R6 here. But I have to find Norton's current and I have to find Norton's resistance here. So Norton's current is found by, at this point, I short this thing here. So we short from here to here, we short it, and we get this circuit here to find Norton's current. And Norton's resistance is remove the voltage sources, same, and find out what is the Norton resistance here. So this is a 3-node circuit. This is 1 node, this is 2 node, and this is, well, I've written 2 node, but effectively this is also a 3 node. 1 node. R1 parallel R2 is, so you can remove this particular node here and effectively it can be solved here. So one application of Norton's theorem results in decreasing the number of nodes from 3 to 2. You apply Norton's theorem to this one again. So you apply it here. So this becomes the eventual circuit. And to find out IN2, you short it, you have to solve this one. And to find the Norton's resistance 2, this is the circuit that you have to solve. So a 2-node circuit becomes effectively a 1-node circuit. So again, what we are doing is, one application of Norton's theorem results in effectively solving a 2-node problem. Another application of Norton's theorem results in solving basically 1-node problem. So every time you're applying a Norton's theorem, effectively what you're left with is a problem of complexity n-1. If n is the complexity of the problem here, you're left with n-1 complexity here. And once more, then n-2 and n-3 and so on and so forth. So again, same thing, circuit complexity, n-1 node, n-2 nodes here, one more application. Eventually, if you keep on applying it, all you have to do is you have to solve, not one mesh, but 1-node circuit. Eventually, you'll be left with a 1-node circuit, several of them, but each one of them you can solve by simply looking at the circuit, you can write down what the answer is. Because often it's a voltage divider kind of a thing. Voltage divider or a current flowing through 2 parallel resistors. So straightforward circuits are there, which you can solve by simply looking at it, you can write down what the answers are. So, similarly, in Norton's theorem also, this is the result that we get, and this is the result that we get otherwise here. So you get a structured expression, which gives you more insight and helps you understand the relative importance of different variables which are there in a much better. For example, if I look at this expression, I see R1, R2, R3, R4, all of them are all over the place. But this shows you that R1 is in parallel with R2. If R1 is, let's say, if R1 is 100K and R2 is 1K. If R1 is 100K and R2 is 1K, I can't see much in terms of what is happening here. But I know that everywhere where R1 and R2 is appearing, they are parallel. Say one of them is 100K, the other one is 1K. Effectively, I know R1 doesn't matter. R1 will drop out from here, R1 will drop out from here, will drop out from here, drop out from here. The only place where it matters is here. Okay, so we can very quickly see what the impact of a particular resistor is, while here, it's all jumbled up. You can't see what the importance of different elements are. Okay, so the Thevenin's theorem then simplifies circuit analysis by reducing number of meshes in circuit by 1. Norton's theorem reduces number of nodes in the circuit by 1. Recursive application of these theorems, apply them again and again, can be used to simplify the circuit sufficiently so that they can be solved by inspection. That's the goal. In fact, in all of the hand analysis, that, the circuits that we analyze by hand, our goal is not to write down all the meshes, all the nodes, and write down all the equations. We don't want to do that. We want to transform the circuit so that we can solve by, this is the eventual goal. Transform the circuit by applying Thevenin's, Norton's, source transformation, the different techniques that are there, series, parallel, and star, delta, all of those techniques that are there. We want to use those techniques, transform it so that we can eventually obtain a circuit which is simple and we can solve by inspection. The other interesting outcome is the application of Thevenin's theorem is like performing algebra on the circuit. Okay? What do we mean by that? Let's see. Suppose you were trying to solve this particular circuit. Okay? By a normal mesh technique here. So what we would have done is we would have written KVL in this mesh, KVL here, KVL here. And we would have obtained these three equations. Right? In each one of them, we would have written a mesh equation here. So that's the first mesh here. I2 minus I1 R2, I2 times R2 plus R3 plus R4 minus I3. The source is minus V2. You can, of course, write it in different ways. You can take V2 on this side or this side. So that's for the second mesh. And for the third mesh is over here. Okay. Now, that's, as we said, circuit analysis is transforming a circuit into a set of equations and solving those equations. Right? So now how would you solve these three equations? We have three variables, I1, I2, I3. So how would you solve? What would you do? Well, multiple ways. I could say, well, I have three variables, I1, I2, I3. Let me eliminate I1. Right? Let me eliminate I1 from my set of equations. If I do that, if I eliminate I1 from my set of equations, what will I end up with? I'll end up with two equations in terms of I2 and I3. Can you see where we have gone? I've taken an equation, set of equation with three variables. And I try to solve it by algebra. So I eliminate I1. If I eliminate I1 by multiplying here and there, I'll end up with two equations in terms of I2 and I3. Two equations in I2 and I3, what does it represent? Three equations, what do they represent? Three mesh. Two equations in two variables, what does it represent? Two mesh. Right? So let's do that here. Let's look at I1, I2, I3. Let's eliminate I1 from equation 1 and 2. Well, so we write the I1 here in terms of this one. We substitute it back in 2 and 3. And we get these equations. We get I2, I3, here I2. So we get equation only in I2 and I3, as expected. Now, interestingly, we are saying that you can take a circuit and transform it back into equations. But the reverse may also be true, right? I can take an equation and transform it back into a circuit, represented in the form of a circuit. So these two equations that you see here, I can represent it in this form. Check it out whether this is true or not. Look at these two equations and see whether this circuit represents these two equations. Look at the term here. This term, V1, R2 by R1 plus R2 voltage sources minus V2, this and this. The resistors are R3, R4. You can check it out that these two equations, after I eliminated current I1, I ended up with two equations here. And these two equations are this one here. Can be represented in this circuit form. Now, if I took, fine. So we said that if I transform it into a set of equations, eliminate variable I1, I get two equations, and two equations basically represent the circuit. Now, look at this particular one. If I apply Thevenin's theorem on this part of the circuit here, if I apply Thevenin's theorem, what will I get? Apply Thevenin's theorem only to this part. You'll get VTH, RTH, R3, R4, V2 here. And VTH is V1, R2, R1 plus R2, RTH is R1, R2, R1 plus R2. All right. So what happened? In the sense that I'm transforming a circuit into a set of equations. I'm performing algebra on them, eliminating variable I1, eliminating variable I2, and eventually finding the answer, right? As an intermediate step and I eliminated I1, I've showed you this circuit here. That the equation that I obtain is same as this particular circuit. On the other hand, if I take my original circuit, apply Thevenin's theorem to a part of it, I obtain this, which is nothing but this. So in effect, can you see a parallel between them? When I'm taking a set of equations, I'm performing algebra on them, I'm eliminating variables. From 3 variables, I get 2 variables. Is similar to, I took this 3-mesh problem here, applied a Thevenin's theorem to a part of it, eventually reduced it to a 2-mesh or a 2-variable problem. So what you're doing in terms of algebra, there's a clear parallel in terms of what you're doing when you're applying Thevenin's theorem. It's a similar. So another way, as I said, what we can say is Thevenin's theorem is like performing algebra on the circuit. You're not directly taking equations, manipulating them, eliminating variables. What you're doing is, well, let me apply a Thevenin's theorem to this, and I end up with this particular one. And as you can see here, when you take this very simple case, the Thevenin's application of Thevenin's theorem is straightforward. You can very easily write what is VTH and what is RTH here. Very easily write, and you end up eliminating basically the mesh 1. Mesh 1 you end up eliminating, and you get 2 meshes here. And so the process is similar. All right. So another way of looking upon is that when you're eliminating variables and trying to solve it, what you're doing is maybe performing, using Thevenin's theorem, performing algebra on the circuit itself. Okay. All right. So the two equations are similar, and that's two perspectives. Then one is what is really happening when you apply Thevenin's theorem. You're reducing the number of meshes by 1, effectively transforming a n mesh problem into n minus 1. What is happening with Norton's theorem? You're taking an n node problem and transforming it into an n minus 1 node problem. And you can keep on doing it and thereby eventually obtain a set of very simple circuits which you can solve by inspection.